Of course, A and H and K need to be real numbers, and A can't be 0, because if A was 0, then all of this would just be canceled, and then it wouldn't be a square anymore, and then it's not a quadratic, and so like, what's the point of anything if A was 0, right? Of course, it's called vertex form because when you look at it, you get to see the vertex. So vertex being H, K. So there's the vertex right there when you look at it. Of course, the Y can sometimes be called transformation form because H controls those left and right shifts, and then K controls those up and down shifts, so those transformations. And then A controls that vertical stretch, compression, reflection business. So seeing how it deals with the transformation, so Y might be called transformation form. The axis of symmetry, of course, is that line that goes through the vertex. And last time we saw how we needed to find that first, and then we found out where the vertex was on that line. This is kind of backwards. We know where the vertex is, and so then we know where the axis of symmetry is because those two things are always the same. So whatever your H value is, is automatically your axis of symmetry there. X-intercepts, that's a little bit more complex this time. But again, when it's set equal to 0, so you set the equation equal to 0 and you solve for x. Just remembering that when you're solving and if you square root both sides, that you do need to have that plus minus sign. Run into that later. Then the y-intercepts, not too bad for this. With the last form, we saw that it was just the c value. This is not that way. So what we always know about y-intercepts is that x is 0, right? And so we know that. So if we know what x is, we plug it in and it spits out a y. And so that's what they're trying to get at here is that your y-intercept is 0, whatever. So plug in 0, see what you get. And that's the y-intercept. So it's not k, right? So they use a different letter there for a specific reason. That k and c don't have anything to do with each other. So a couple of quick things there. Does anybody need more time for me to go back over any of that part? So move down to the bottom of that page. Look at a couple features. I left out the x-intercepts on purpose. This problem does not lend itself well to doing the x-intercepts just because it gets really messy, but we'll do a couple of those in a second. So vertex, of course, again, HK. Remember that H is a liar. So it's positive 2, negative 4. Okay. Axis of symmetry, super easy, right? Just whatever that x value is. But remember, it needs to be written as an equation because it is a line. So it can't be written as a number or a point. It's an equation, so it needs to have or it's a line, so it needs to have an equation. So x equals 2. Y-intercept, that means we know that x is equal to 0. So I'm just going to say that y equals 3 times 0 minus 2 squared minus 4. And then you just simplify that down, okay? So since we're simplifying, that means we're looking at PEMDAS. So inside your parentheses first, which means that we're looking at 3 times negative 2 squared minus 4. And then we go to exponents next. So we're doing this. And negative 2 squared is not negative 4. It's positive 4. So we get 3 times 4 minus 4. And then we do multiplication. That's 12 minus 4, which of course is 8. That means our y-intercept is at 0, 8. Our x-intercept, x value was 0. So pretty easy to find y-intercepts. What about our domain? What's our domain for this? You're saying all real numbers, okay? So what does that mean when we say the domain is all real numbers? When we look at the graph, what does that mean? If we know the domain is all real numbers, what are we going to see on the graph? Or what would we have seen on the graph to tell us that it's all real numbers?
Can you repeat the question?
We know the domain is all real numbers. What does that mean about the graph? What are we going to see on the graph? Or what would we have seen on the graph to know that the domain is all real numbers?
The x-axis will go on forever.
Try to word that, Grant. The x-axis always goes on forever, no matter what we're talking about, because it's an axis. It is a parabola, but that doesn't. It's not what I'm asking about. The domain is all real numbers for no matter what function we're talking about. What does that mean graphically? What would the graph look like for any function whose domain is all real numbers? Okay, can you be more specific, Victoria? Their arrows? What about those arrows? Again, that'd be a better thing to put in the public chat, Victoria. Okay, so on the graph we'd have arrows on the ends. But what about those arrows? What are they? What's this negative infinity, positive infinity mean? If you guys looked at a graph, how would you know that the domain was all real numbers? Or since the domain is all real numbers, what do we know about the graph? So Victoria's kind of hitting on it with this, that the ends have arrows. I'm trying to get a little more specificity out of it though. But if we're talking about domain, don't say the word it. How do you want you like? I'm trying to get you guys to be more specific. So using the word like it doesn't help us talk. Be specific. What do x values do? Which way do x values go? Okay, so Adam, you're kind of getting at. Probably should scratch the part where you say on the x-axis. Okay? The graph wouldn't have to be on the x-axis, but just when you say left and right, I think I know why you meant to say that. But yeah, since we're talking about x values, we're going left and right forever, right? The negative numbers and positive numbers forever. So that idea that the graph would go left and right forever. Okay, so those arrows, like you're trying to say, Victoria, right? That's all I was really looking for you to add on your statement, Victoria, is that it would go left and right forever. Add in the direction of your motion. Because technically, something like this does go forever. It only goes one direction forever, right? So you got to be more specific that it's both directions. So that's all I was looking for you to be more clear on. So that's what it means graphically. But what about the function itself? For us to say that the domain is all real numbers, what do we know about the function? So I'm kind of making up a word here, functionally. So if that's what we know about it graphically, what do we know about it functionally? How does domain relate to the function? So I'm trying to pull this apart from the visual side of the graph. What do we know about the function since the domain is all real numbers? Trying to get if you guys actually understand what domain and range are actually about. Write it down, but if you don't know actually what it means, it's kind of what's the point? If we know the domain of a function is all real numbers, what does that actually mean about the function? Okay, so any x value can be plugged into the equation. What happens when we plug in those x values, Adam? If we're plugging numbers in, what are we expecting to happen? Okay, then we're going to get an output, right? If we're plugging a number in, we're expecting something to come out, right? So it's telling us that any number can be plugged in, like you said, and that they will all give us answers. Right? So why am I pressing you guys on that? Are there functions that we can't plug any number into? Is it a big deal for there to be all real numbers? do you think, Tiger? Is there a function that we can't plug just any number we want into it? What do you think, Riley? Are there functions that we can't just plug any number in? Katie? Like what, Katie? What can't we plug a number in? What functions can't we just plug any old number into? Yeah, right. Yeah, there you go, Tiger. Square root functions, right? Can't square root every number there is, right? We try to square root certain numbers and we don't get answers, right? There's another one that we've talked about too, right? Rational functions. Right? 1 over x. What number are we not allowed to divide by? Yeah. So there's certain functions where we can't just plug anything we want in, okay? Because some of the numbers don't have answers, right? So we're saying for this function specifically, and most functions, that we can plug in any number and they will all give us answers. Just really understanding what does domain mean. It seems like you guys are struggling with that. Okay? We keep talking about it, but do you actually understand what it means? Okay? It's a big idea. Are you actually holding on to that information? Okay. So graphically, we should see the arrows pointing left and right forever. Functionally, we can plug in any number we want and we always get an answer. Doesn't mean it's a pretty answer, but it means it's an answer. Okay. Just because the math isn't pretty doesn't mean there's a difference between getting an ugly answer and getting no answer at all. Okay. There's also a difference between getting 0 as an answer and getting no answer. Okay. Getting 0 as an answer does not mean that there's no answers. Okay. So range. Right? How do we do this without having to graph it? Okay. So what do we need to be thinking about? Right? So Rhea earlier said this is a parabola, right? We know something very specific about parabolas, that they either open up or they open down, right? So how do we know if the graph opens up or down? Because our range is about our y values. How do we? And that's an up and down idea. How do we know if our graph opens up or down? Both of my other classes have been able to get through this pretty quickly, guys, and I'm a little tired of having to wait so long for answers from you guys.
If there's a negative in front of the equation.
Okay. More specifically, which letter should you be looking at, Maddie?
The leading coefficient.
Which letter?
A.
Yeah. So if our A is negative, then the graph opens down, right? If A is positive, this graph opens up, right? So our A value being 3 is positive, so that means our graph opens up. Well, if our graph opens up, that means it has a what? What's that called? If our graph opens up, then it has a what? Matt, Marlo, Riley, Jaden. Yeah, Victoria, minimum, right? So that means that our graph has a minimum. Okay, so that our lowest point, which would be our vertex, it's also the minimum. Okay, well, the value, since we're talking about range, is the y value, the -4. So because that's the minimum, that means it's the lowest value in our range, and it would go up forever. Okay? So if we don't want to graph it, we have to think about it. This graph opens up, has a minimum, that means my y value is my lowest value, so it should start my range, right? So if, right, a was less than 0, so if it said -3 instead of +3, that means our graph would open down. which means it has a maximum, right? Which means that our y value is now the highest. Okay? And so that means that that -4, if it was the same vertex, would now be the highest value of the range, and then it would go down forever. Okay? So if domain describes our inputs, what they can be, okay, then the range describes our outputs and what they will be. Okay? So this would say that all of our answers would be -4 or greater. We would never get an answer that's less than -4. Okay? Or this would say all of our answers are -4 or less. We would never get an answer that's more than -4. Okay? So that'd be like the function side of things. Right? This describes what we can plug in. This describes what will come out. Okay? Inputs versus outputs. Okay? So how do you think about it instead of having to actually graph it? Okay? So you guys can figure out the range without having to graph it. Make it more abstract. Anything about any of that stuff you guys want to talk about? More detail? Jaden, you there? Riley, you there? Marlo, you there? Matt, you there? Cole? Caleb? Colby? Kayla? Angelique, you guys awake? Don't feel like you are.
Yes, Mr. Baker, I am awake.
So we're going to go off script here for a little bit. Okay, so we're going to use one of the blank pages in your notebook to do this. So we're going to find the x-intercepts of these two functions if you want to do both of them. So remember what that means to find x-intercepts is that we're looking for whatever x value makes y equal to 0. Okay? So our first step is to make y equal to 0. And then you're going to solve. And since we're solving, we're using SADMAP. Okay. So let's get x by itself. So any subtraction, addition that needs to go away first. And then I want to get rid of any multiplication, division. So get rid of the -2. So that's equal to 16, x minus 3 squared. Now we're down to the exponents level. Okay, so get rid of the exponent. So of course we square root both sides to do that. So on that right side, we square root. There's no more square. There's nothing on the outside of the parentheses anymore. So the parentheses are useless. So we don't need those anymore. On that left side, so remember what this is not. This is not me saying what's the square root of 16. This is me asking you what number squared is 16. That there are two answers to that question. Okay? The problem did not say what's the square root of 16. We put that square root in there. So we have to address the fact that there are two answers to that question. Okay? And so as we write 4 here, okay, we also need to write plus minus. Okay? So when you decide to square both sides, you must put in the plus minus. Let's get this to be over again, isn't it? Okay. And at that point, you just need to break the problem into 2. 4 equals x minus 3, and -4 equals x minus 3. So adding 3 to both sides, we get x equals 7 and x equals -1. I know last time it asked you guys very specifically to write the x-intercepts as coordinate pairs. Also, you had to write like the small one first and then the larger one second. This one asks you to write the answers as a comma-separated list. So you're not writing 7, 0, and -1, 0. Okay. All you're going to do is say x equals 7, comma, -1. Okay? And it's not parentheses. It's not an interval. Okay. It's a comma-separated list. There's nothing around those. Okay. That's all you have to do. And I do not believe that the order you write them in matters at all. Okay. Anything about that you guys want to talk about? You guys want to do another one, or is that enough? Okay. Can you do real? So start off the same way. We need y to be 0, right? Remember this whole thing is y. So it's not f of 0, it's the whole thing becomes 0. Okay, what's our first step? A 12. Okay. What's next? Multiply by 3. So 36 equals, right? Why did we multiply by 3? To cancel the 3 that was dividing. So we still have 4 times x plus 2 squared. What's next? Divide by 4, right, Jordan, right, Victoria? So we get 9 equals x plus 2 squared, because that just canceled that. What's next? Square root both sides, right? Sure, Matt. Yeah, remember when we square root, we got to make sure we put the plus minus. And then we break it. So 3 equals x plus 2. Negative 3 equals x plus 2. Now, what number do we add to 2 to get 3, right? So, of course, x is 1. What number do we add to 2 to get negative 3? It would be, negative 5. Definitely nothing that you guys haven't done before. Okay? Solving equations by using square roots. You guys have done. Or you could have done that one differently at this step. There was a choice Maddie made, kind of led us down one path versus another. Could we have done here instead of dividing by 3 or multiplying by 3? How can we get rid of that all at once instead of doing it in steps like Maddie had to? Nothing wrong with it, but just something different. Yeah, right, or multiply by reciprocal. Right. So take that times 3/4. Right. So of course on that right side we end up here, right? And then you figure out what 12 times 3/4 is actually pretty easy. Right? Remember the 4 is dividing. Okay, so 12 divided by 4 is 3 times 3, right? So 3 times 3 is 9, just like we had. So 3/4 of 12 is still 9, right? And then you just move on from there. So multiply by reciprocal instead, but both ways work. Right? Actually, usually see more students be successful doing it in steps than this, but just something to think about. Different way of approaching it. All right, that's it for that piece. And then last thing, so on the last page of your notes for this section, you guys should have these two graphs there at the bottom. So on this page, you should have these two graphs. You guys all find that? All right, so they want to start the equation of this function in vertex form. So it's going to be y equals a times x minus h squared plus k. All right, and so for us to be able to do that, we need to be able to figure out what a and h and k are. Okay. Once we know those three values, we just plug them in. We're done. Okay. Well, h and k are the easiest piece of that. Right, that's the vertex. So going there, identifying your vertex right off the bat. So that's at 2, 7. So there's my h value, there's my k value. Okay. I showed you guys a different way of doing this Thursday. Okay, I'm going to show you a different way now to do this. Right? More of an abstract way, a thinking way, rather than a doing way. So the way I showed you guys on Thursday was very concrete. Do this, do this, do this. You get your answer. Here's let's stop and think about this. Right? So knowing what we know about A, right? A has two jobs. It's either reflecting or it's compressing, stretching. Right? So we can definitely, as soon as we look at this, we're like, we know A is negative. There's no way it's not. Okay. The stretching and compressing part is harder to see. Right? Is this graph being stretched? Is it being compressed? It's harder to see. And so what sometimes is easier to do is if I go and compare it to the parent function, it makes it a little bit easier to see. So I'm going to bring in the parent function here real quick. So you guys don't need to do this. We don't want to. Don't really have space to do it, so it's going to be kind of hard for you to do it. So if we think about the parent function, right, just good old x squared. So it starts at 0, 0. And then if I plug in 1, I get 1. If I plug in 2, I get 4. And if I plug in 3, I get 9. And same thing on the other side, y-axis. Plug in 1, negative 2, negative 3, right? So remember what stretching and compressing does. It takes the way that the y value should grow and changes it. It makes it smaller or greater. Okay? And so what we need to think about is how should the y values act when we change x values. And so I'm going to zoom in here a little bit and say, as we change x, right, we get to pick what x is. X is our independent variable. It's the one we get to pick. So as I go over 1 in the x direction, how does y react? Okay. So as I go to the right 1 or left 1, since it's square, it doesn't matter what direction I go. But as I go right 1, the y value then reacts by going up 1. Okay? That's the normal way that it acts. I'm going to do this going left on the next one just because so my writing doesn't go over it. Okay? Again, since it's a square, it doesn't matter if I go left or right, the y acts the same. Okay? So as I go right 2 or left 2, how does y react? Y goes up 4, right? Makes sense. Change in 2, 2 squared is 4, right? So this is what the y values are supposed to do with certain x changes. If I change the x by 1, the y value will also change by 1. If I change the x by 2, the y value will change by 4. That's the way it's supposed to act. Right? That's the parent function. Okay? Well, what's our function doing? Now, since I already know a is negative, I'm going to ignore direction here. I'm purely going to be talking about the magnitude of the number. How big is the number? How much is things changing? Not the direction of its change. Okay? So as I go to the right 1, what's my graph doing, right? Is it moving 1 down this time instead of 1 up? Right? Is there a point there? No, there is not. Okay, our graph is not doing that. What is it doing? That sends me down 2. So going to the right 1 has caused a y value change of 2, not 1, like it was supposed to. I'm going to look at the other side also, and just, again, what happens if I change it by 2? Changing by 2, again, doesn't matter what direction I'm going, left or right, because it's a square, it always acts the same, was supposed to give me a y value change of 4. But there is definitely not a point right there. How far do I have to go to get that next point, which is down here? Yeah. How far is that? That's 8 units away. So an x value change of 1 was supposed to change my y value by 1, but it changed by 2. An x value change of 2 was supposed to change my y values by 4, but it changed it 8. So what's happened to my y values? How are they reacting compared to how they were supposed to react? By changing x1, I was supposed to get a y value change of 1, but there's this a value here. It's doing something to it. Okay? So it's not changing 1, it's changing by a factor of 2. Okay? I'm supposed to move 4, but instead it moved 8 because the a value is multiplying it. So can you guys see that those y value changes are twice as big as they were supposed to be? It was only supposed to move 1, but it moved 2. It was only supposed to move 4, but it moved 8. You guys see that? Anybody out there? So this is the thinking way to do it. What was the y change supposed to be? What is it? What number would I need to multiply that by in order to get it to do what it's doing? Remember, it's a multiplication thing. It's not an adding, subtracting thing. I had to multiply. It was supposed to be 1, but it was 2. That means I multiplied by 2. It was supposed to be 4. It was 8. That means I had multiplied by 2. Okay. Try it again over here. So I need to know a, h, and k still. Again, I always start with the vertex. Vertex is at 3, -1. So there's my h. Here's my k. Now I'm going to zoom in and look at those changes in y in relation to changes in x. So as I go to the right 1, it's supposed to go up 1. It is not doing that. It's somewhere in the middle there. Okay? Not quite sure what it is. Okay? So these fraction ones, they can be kind of tricky because you might not be sure what fraction it is. Right? And it's not always safe to assume. So what if I go the other way? If I try 2, change in 2, it's supposed to be a change of 4 in the y value. Okay? Which would get me to here. So it definitely does not hit 4. Okay? How far does it move? only moves 2. So it was supposed to go 4, but it only went 2. What's the ratio there? Right? It was supposed to go 4, but it only went 2. It only went half as far as it was supposed to. Okay? Does that make sense over here? It's supposed to go 1, but oh, yeah, that looks like half. All right, so I have something else to judge it off of besides a point that's in the middle. Okay? So if you have a fraction movement, I wouldn't judge it off that because you can't tell the difference between half and like 2/5. With our eyes, we can't do that. Okay? So I'm using a different point where I can get an exact number and then look at the ratio. Okay? It's supposed to go 4, but it only went 2. That means it moved half as much as it was supposed to. All right? So A is 1/2. Right? A is also positive because it opens up. So we already knew that. Okay? So we know A is positive. We know A is causing a shrink in Y chain, just half as much it was supposed to. We have our H and our K. Okay? So Y equals A positive 1/2 X minus Y value is 3, or sorry, H value is 3. Remember, if that had been -3 or something like that, you'd have minus -3. This would need to say plus. Okay? Squared, and then plus -1. Of course, we don't say plus -1. Okay? Say -1. So that's the abstract, that's the thinking way to do that as far as finding the equation from a graph. The other way I showed you guys on Thursday, if you have the vertex and then one point, doesn't matter, just find a good point. There's lots of good points here. Okay? So something like 5, 1. That's a y value, a x value, minus your vertex, and then solve for a, and then you plug it back in. Solve for a, figure out what it is, then it goes back in. That's the doing way. Find the vertex, find another point, plug it in, do all the arithmetic, versus the thinking way, which is what I was trying to show you guys there, how to be more abstract. Being more abstract will be faster. And you guys worried about doing your ACT, right? Speed is a big deal with ACT stuff. So trying to think about stuff instead of doing stuff will make you faster at it.